In this video, we will discuss about the condensation of water vapor inside a headlamp. Okay, so this is the sample geometry what I have considered, and you can see I'll just hide this face outside the body. Sorry, go to face, hide face. So this is the headlamp, and this is the lamp, and remaining everything is the glass that is covering it, right? And to this portion I will giving a lower temperature, maybe less than 10 degrees, and there is a heat that will be emanated from the this internal lamp section, from this lamp section. So I have just named it as, this is a cold part as just a naming section, and this is a filament. Okay, so after that you can just go to mesh, and in this particular video I will showcase you that how it will condense with respect to VOF. In the next video I will showcase you how we can handle water vapor as a individual GPM particles, and those GPM particles going and sticking on to the cold part or else filament or any other part due to the temperature gradient and pressure gradient. On the deposition of those DPM, that will be converted into a Eulerian wall film, and if the Eulerian wall film thickness is crossing a particular limit, then it will be a, so I'll try to mesh here, increasing the double precision. I'll be using 4 core as it is the student version. It will take some time to open. So meanwhile I'll take the snip of this. Just copy it in the paint. It's got open, so I'll just close this space climb. So import geometry. So as you can see here on the screen, so this entirely will be at a lower temperature, this film will be at a higher temperature. And I'll patch the entire area with some water vapor fraction. And of course, along with water vapor, there will be nitrogen as well as some oxygen. This is the total entire air. So this water vapor fraction need to be patched according to the relative humidity or the humidity content that is present inside the headlamp. Okay, so now when the vapor that is present inside the chamber, if it reaches below the saturation temperature, for the corresponding saturation pressure of water vapor, not the total air, it is only of water vapor. Saturation pressure of water vapor, then vapor starts condensing. So for particularly, in order to have a relation between this pressure and temperature, so there is a regular equation called Antoine equation. I have already stated this in many of my previous videos. Antoine equation. So you can just go to Google and you can search also. Antoine equation. We'll get that. So this is a relation between absolute vapor pressure of water vapor, and this is the temperature at which it is prevailing. So if the temperature decreases, what happens to the vapor pressure? If the vapor pressure increases, what happens to the temperature? So for the corresponding temperature, what is the vapor pressure? So accordingly, we'll have a relationship, and that relationship you can just check here. But these are relationship for the saturation temperature, UDF, in order to have a relation between saturation temperature and water vapor pressure. Okay. So now you can just update it. You can now have only curvature with 30, and I will try to decrease this to 1. Generate surface mesh. So it will generate the surface mesh. Describe the geometry. So there are only fluids. Change the distance. If there are two fluids, the relation between two fluids should be have an internal interface, not a wall. And I just want to apply the shear topology. Describe the geometry. Apply shear topology. It's okay. Then cold part is also a wall, and filament is also a wall. Both are walls. Update geometry. Update geometry. And we don't want the filament, right? So this should be dead. So filament is just a wall, right? So this is dead. The internal volume of the filament we don't require. Update. And yeah, time being, maybe I'll give 3 transition layers, and then generate volume mesh, generate the volume mesh. It will take some time to generate the volume mesh. Then after, you need to click switch to solution in order to get into the solver mode. Okay. I have activated the gravity, which is in minus 9.81 direction. You can see, so it is a y minus 9.81. And in the models, I have activated the mixture model. Right. So in the mixture model, you need to activate the water liquid as one phase and secondary phase as air vapor. So in the air vapor, so there are 3 components: water vapor, oxygen and nitrogen. So as it is clearly shown on the UDF, so this is the primary phase thread, that is for water liquid. Secondary phase thread is for air vapor. In the secondary phase thread, we are trying to select first element. The first element is water vapor. So this helps in getting the water vapor pressure. The water vapor pressure, if it is measured and it has some value, with respect to that value we'll get the saturation temperature. So now if you go to the boundary conditions, here you can see cold part is maintained at 1 temperature, which is 278 Kelvin that I have given, and on to filament, which is hotter than the cold part, have given a heat flux of 7000 watt per meter square. Okay, so now with respect to that, I have been starting the transient simulation run, and before that we need to go to multi-phase. In the phase interaction, it's the phase to water vapor to water liquid conversion depending on the user defined saturation temperature, which I have already hooked through the UDF. The UDF, you can just go to user defined functions, compile, add, and this lib UDF, you can find this path. So you can just build and click on load. Automatically it will be loaded, right? Then you need to click on initialize. With initial water vapor fraction is 0.008, and this is also in fraction. Initialize and click on run calculate, right? This is the time step size what I have selected. Now you can, after some time for run, I'll just highlight how these cold and film parts will look like. This is how the saturation temperature is. Both are near to the same temperature, saturation temperature, but this is at a higher saturation temperature value due to the vapor content that is being transferred due to the temperature differences. And just activate these planes, you will understand how the velocity of the mixture is present. So you can see this is the velocity of the mixture that is present. If you want to see only phase 2, that is air vapor, you can observe. So air vapor mixture has more velocity near to the filament because due to the higher temperature gradients. And now if you can observe the phase fractions also, so there is more phase fraction of phase 2 all around, but at the filament it is low in value. Now we will check phase 1, that will be more relevant. So here you can see formation of water liquid to very slight extent. You can just, maybe we can have the focus on these two, and I'll decrease the values. So this is where how the condensation is occurring. You can see here the condensation started, it's occurring on the filaments as well as headlamp. Okay, so now we'll go to the next part of the video in the next session, where we'll consider the eulated wall film through DPM. So instead of water vapor treating it as a continuous media, we will treat it as a discrete phase particles. How the discrete phase particles deposition will go, okay, onto the filament and as well as cold part. Thank you.